In this problem, the book has given you a molecular formula which corresponds to an aromatic hydrocarbon, and they tell you what kind of product distribution you get, like how many products you get when this compound undergoes a bromination or a nitration, and depending on the number of products you get, you should predict the structure of this molecule. Alright, so the information you have here is that this is an aromatic hydrocarbon, so which means you should have at least one benzene ring, right? You should have at least one benzene ring, and the formula given is C8H10, so C8H10, and if you try to find the double bond equivalence, you should understand that the corresponding straight chain alkane is going to have 16 hydrogens, you are actually 18 hydrogens, my bad, right? And that means you have 8 missing hydrogens, so 8 divided by 2 equals 4, so the double bond equivalence is 4. And if you look at the benzene ring, it has one cyclic structure which corresponds to one double bond equivalent, and you have 3 double bonds, so all in all you have 4 double bond equivalents in a benzene ring. Therefore, for this molecular formula, you cannot have any more double bonds in this molecule other than what you have here. So if it's a hydrocarbon, aromatic hydrocarbon, and it has 6 carbons already, you can only have 2 more carbons. So you can write several possible structures for this. So I can put an ethyl here, that's carbon 1, carbon 2, and if you count this will be C8H10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That's what. So you can have an ethyl benzene, or you can have dimethyl benzene, which is a xylene, right? Which is a xylene. So you can have paraxylene, you can have metaxylene, or you can have an orthoxylene. And from now on, I'm just going to draw a circle here to represent these 3 double bonds. So you can have the metaxylene. These are the possible structures, and you should try to see which one of these can give you 2 possible ring substituted monobromobenzene derivatives, right? So when you brominate this and you put only one bromine in it, and with FeBr3, you should be getting monobromo product, FeBr3, right? You should be getting monobromo products. But when it comes to ethyl benzene, it should give you at least 3 possible products, right? So when that is ethyl group, that's 1, that's 2, and that's 3. So there are 3 possible places where you can put a bromine that will give a distinct product. This and this are the same, this and this are the same, therefore 3 possible products. But the problem states that this C8H10 molecule gives only 2 possible products. If you take the paraxylene, as we just saw in the previous problem, this is same as this carbon, which is same as this carbon and this carbon. So monobromination of paraxylene is going to give you only 1 product, right? Because they're all the same. When it comes to metabromobenzene, this is different, this is different, and this is different. So this is location 1, let's say, location 2, location 3. These 3 are distinct centers. This carbon and this carbon, they are the same, therefore they will not give you different products, whereas when you do a monobromination, you get 3 possible products out of this. So this is 1, 2, and 3. There is only 1 distinct carbon in this molecule. Whereas when it comes to orthoxylene, that is carbon 1, location 1, which is same as that, and this is location 2, which is same as this, and there are no more distinct carbons in the molecule. Therefore, if C8H10 is going to give you only 2 monobromo products, that's going to be the orthoxylene molecule, and we can draw the structure here to make sure that we understand what's going on. So if this is orthoxylene, that's 1 bromo product upon monobromination, and the other structure you get is going to be that. And if you put a bromine here instead of here, that is the same as this molecule. If you put a bromine here instead of here, it's the same as this molecule here. Okay, so that's the structure of C8H10 that gives 2 monobromo derivatives. And C9H12 is the next structure that they give you, and they say that it can give only 1 mononitration product. Alright, so they're doing a nitration of this ring, and if you look at C9H12, compare that with C9H20, again a difference of 8, which means that corresponds to 4 double bond equivalents. That means you again have one benzene ring which corresponds to 4 double bond equivalents, and then you have 3 more carbons to add to this benzene ring. So 3 more carbons and hydrogens corresponding to that, right? So again, I'm going to just draw a circle in the middle so we can avoid any confusion about the double bond being conjugated, right? So let's say we take this example. So 1, 2, 3 hydrogens, and each of these carbon has 3 hydrogens. So this is 9 plus 3, 12, right? So this is C9H12. But if you do this, if you take this ring and you do a nitration, which is H2SO4 and HNO3, it's going to give you two possible products, because that is carbon 1, location 1, which is same as this, and this is a different location. That means you have 2 possible products you can get out of this reaction, which is not what we want. So just to make sure you guys know what I'm talking about, right? So these are the 2 possible products, and therefore therefore this structure is not going to give only one product. All right, so this is not the right structure for C9H10. So let's now take another possibility. Let's make this molecule completely symmetrical, so like that. Okay, so this carbon is same as the carbon here, same as the carbon here. So there's only one location in this molecule which is going to react, because all of the other locations are the same as this one, right? And therefore H2SO4 HNO3 is going to give you only one mononitration product, right? And that's the structure of C9H12, which is this structure here. Any other isomeric structure of C9H12 you write is going to give you more than one product upon mononitration. Okay. C9H12, one more structure, C9H12, can give 4 mononitration derivatives. Just as we saw in this case, C9H12 is going to have 4 double bond equivalents, which means you need to have a benzene ring with 3 other carbons attached to that ring. Okay, either as 3 methyl groups, or could be a propyl group, or it could be an ethyl and a methyl group, right? So it gives you 4 mononitration products, and let's say we take a structure like that, right? So I'm just randomly starting this, and if you look at this, this is a distinct unique carbon, unique locations. That's 1. This is a unique location as well, so that's number 2, right? And that's number 3. Okay, there are only 3 different locations in the molecule, and all of them are different, but you can get only 3 products. You cannot get 4 products. All right, so this is not the right structure. So let's try another example. So you just have to do this trial and error, and of course you kind of have to have a sense of the symmetry in a molecule, right? So let's try perhaps that. So once you put 3 methyl groups, you can realize the maximum number of distinct unique locations you can have in a molecule is 3 and less than 3, right? Maximum is 3, and you'll end up having even less than 3 perhaps, as in this case, because these 2 carbons are the same. So this is the same and this is a different one. So there are maximum of 2 centers here, right? So when you have 3 methyl groups, you cannot have 4 different mononitration products, which means probably we should open up one more location in the molecule. Therefore, I'm going to combine the 2 carbons, make it an ethyl, make this a methyl. So now this is a distinct center, because if you nitrate at this location, it's going to give you one product. If you nitrate here on that carbon, you'll get a different product. Now this carbon and this carbon, they are the same. This carbon and this carbon, they are the same. Therefore, you don't have to worry about these 2 sides. So this is going to give you 2 different products. But we don't want 2, we want 4. Therefore, the next possibility that I'm going to try is, let's say we put a propyl, like an isopropyl, right? This is also going to be C9H12, but that gives you again only 3 possible different carbons in the molecule. So the next possibility that we should try is perhaps a methyl and an ethyl. So if you try this and you do a nitration and you get a mononitration, then you can see that this is one location. This is not the same as this because this carbon is next to a methyl, this carbon is next to an ethyl, right? Therefore that is 2, so this is 1, this is 2, this is 3, which is different from this center, which is a 4, right? There are 4 different locations in the molecule, therefore you can get 4 distinct mononitration products when you nitrate this ring. So just to make sure, again, you can see this clearly. That is one product. That is different. This is different. This is not the same as this. And finally, we have an NO2 over there, right? So these are all different products, C and D, right? And that's what you need to know for this one.